Does Zoom allow you to do record in high resolution? Chalo, so let's carry on with what we have. Okay, so the big picture then is that we started with a space and we want to define a probability measure. And then we said, okay, the probability measure should have some nice properties, such as translation invariance when you have a uniform measure. And that can't be done on every set, right? So that was the first part of what we did. So we did have to restrict ourselves. So we said, okay, we'll restrict ourselves to sigma algebras, which is a rich class. And then the issue was, how do you assign a probability measure to a sigma algebra? So then we said, okay, we can assign probability measures to an algebra, but there's this very nice Cauchy-Dory's theorem, which extends this probability measure uniquely to the sigma algebra. And we went through the proof. So we saw how that is done, right? So that's where we were. So we could extend the probability measure to the whole sigma algebra. Then we said, okay, let's understand sigma algebra a little bit better. So we saw, Borel sigma algebra on the real line. And then we said, if we want to have a sigma algebra on Rn Euclidean space, then there are a variety of ways of looking at it, and they're all saying the same thing. But we developed our understanding of how to understand, what's going on with these sigma algebras. Then we went further and defined BR infinity, sigma algebra on R infinity. And then we talked about B of RT, sigma algebra when the dimension is uncountable. And so that's where we are so far, right? We've done these things. We've understood the sigma algebras a little bit better. Now we have to get around to assigning probabilities to these sigma algebras. Okay, so that's the agenda for today. We'll assign probabilities to them. Essentially, it's going to boil down to, okay, how do you assign probabilities to an algebra, which is kind of straightforward. You give me a distribution function, I know how to assign probabilities to an algebra, and then I just have to show countable additivity, which we've already shown, at least in the single dimension. But we'll ask ourselves, okay, how do we show countable additivity more generally? And right now we've shown countable additivity for 0, 1. How do we show from minus infinity to plus infinity when we have unbounded support? So those are minor technicalities, but it's good to see all of them, I guess, once. So, hereafter we've seen them, we don't have to worry about them. That's the quality about measure theory from our point of view. We just need to understand it once. And then maybe it's not something we worry about too much. Who knows? I mean, it depends on what you end up working on. I mean, I've had some people who now work in continuous time processes, and they can't help. They have to worry about measurability of every set they consider. Okay, so let's complete what we discussed last time towards the end. So we said, let's take the space omega to be C01, right? So each outcome, each element is a function of t from 0 to 1, and it's a continuous function. It's a path, x of t from 0 to 1. And that's our space. We've collected all those things. It's a great space, particularly for defining Brownian motion at some point. Right? So this becomes a canonical space for it. But in any case, that's a space. So one thing we can do on that space is, now what's a sigma algebra on that space? Now one thought is that we know that we have this soup matrix, the uniform matrix, right, between two elements. The distance between them is basically the maximum distance between xt and yt. Distance between x and y is maximum distance between xt and yt over all t from 0 to 1. That's a metric. Right? So it's a metric space under this metric. And metric space we can define open balls, and we can define open sets. So that's one space that we have. Right? So smallest, I mean, that's one sigma algebra that we have, which is a Borel sigma algebra on C01. Smallest sigma algebra which contains all the open balls, right? Other sigma algebra we can have is that corresponding to cylinder sets, like we did for BRT. Right? We'll just take points T1, T2, some finitely many points, and we'll have cylinders there. Right? We'll collect all those cylinder sets. That's going to be an algebra. And then then the smallest sigma algebra which contains all those cylinder sets. So that could be another thing. And first, we'll just go through the argument just to convince ourselves that both are actually the same thing. Both the sigma algebras are the same. So let's do that right now. So, all right. So here you'll see this is sigma algebra generated by open sets. B is 0. 0 is for open. Huh? I get confused all the time because we have to go back and forth. And then B of C is sigma algebra generated by cylinder sets. We want to argue that B0C is equal to B of C. Okay? So what we'll show that, okay, B of C is the subset of B0C. B0C is again open sets. Okay. That means any cylinder set can be represented as a, a union, countable union, let's say, of open balls, for example. So it's in the sigma algebra B0C.
Sir, sorry to interrupt. Actually,
Yeah.
I didn't know. So where you are taking the open sets in Rn or R3 or something?
Open sets I'm taking in the space of C01.
Okay.
Okay, so the open ball now is take any element and collect all the parts around it.
Yeah.
Some distance rho away.
Yes.
Now that becomes your open ball.
Hmm.
And now open set is just something where every path can be covered with a small ball and you still line the same set. Yeah, right?
Yeah. Sure.
Yeah, so it's a very natural thing to do. Okay, so now we want to show that every cylindrical set is in the B0C, right? So every cylindrical set in the B0C, then the smaller sigma algebra containing cylindrical sets is also in B0C. So B0C is bigger than B of C. Okay, that argument makes sense? Okay. So let's look at this set. XT1 lying between A1 and B1. Now this is clearly an open set, right? Because if I have strict inequality there. If I look at any element belonging to this set, I can construct a tiny ball around it which also belongs to this set. Right? So that's the definition of the set being open. So in particular, now I can intersect this I equal to 1 to n. And this intersection is essentially a cylinder set, right? I mean, now I can do some extra things. Okay, this open sets, I can make them closed by taking countable. I guess if I want to make them closed, I'll take a countable union. No, I'll take a countable intersection from the top. I'll bring it down. Yeah. The complement will also be is also going to be in my, if these sets are in B0C, then their complements are also going to be in B0C. It's a straightforward calculation. You can look at specific things. But this tells you that, okay, cylinder sets, the kind that we discussed last time, which was basically interval cross interval, which is exactly what we have here. These all belong to B0C. So B of C belongs to B0C. And now we want to go in the reverse direction. We want to say B0C belongs to B of C. Right? So now we'll look at a ball in B of C and we'll argue that that ball belongs to B of C. We look at a ball in B0C and argue. So let's look at this ball. So we fixed a point X, right? And we collected all the points YT. So I'm here right now. So I'm looking at this right now. So I've collected all the Ys which are within distance rho from X of T. Okay? So that's a closed ball. If I can show closed balls are in B of C, I can also show open balls are in B of C. So that's, I'll let you do that part. Okay. Okay. But now we know that this closed ball can be represented as countable intersection of these cylinder sets. XTI minus YTI less than or equal to rho. Right, rho was, see, X was given in C and rho was greater than 0. This was given here. So I keep the same rho here. And I look at the cylinder set where XTI minus YTI, I collect all the Y's so the XTI minus YTI are less than or equal to rho in absolute value. This is in my B of C, right? And I intersect over all the TIs. TIs are now taking rational values. Right? This countable intersection over rational is also going to be in my sigma algebra B of C. Right? And this is exactly the same set that I had earlier because of continuity. Right? So it's all the elements in one are in the other. So it's exactly the same set. So then I'm done basically. So all these balls are in B of C, and hence all the open sets are in B of C. Yeah, I mean, that requires a bit of an argument, I guess, that in this space, it's a little bit more elaborate, that each open set is actually, again, a countable union of balls. So, I mean, yeah, I think one has to kind of think a little bit. I mean, you'll again go back to rationals basically, right? But you will think carefully how to do that. But for now, I save myself just by defining B0C to be the smallest sigma algebra, which contains all the open balls. So then, then I proved what I wanted set out to do. But it's a separate exercise to show that open sets are also in the sigma algebra, in the B0C. Okay, so that you can think about. Okay, so we are good on this. So we know that B0C is equal to B of C, right? So that's all I want to talk about in terms of, understanding the sigma algebras a little bit better and their equivalents. Now we'll talk about assigning probabilities to these sigma algebras. So that's our agenda right now. And this, as I mentioned to you earlier, I'm taking from Shirya all of this particular material. Because I mean, it does a very, no other book seems to talk about these things. And it's good to talk about these things. So fx, suppose you give me f of x, which is a distribution function, meaning it's non-decreasing. As x goes to minus infinity, f of x goes to 0. As x goes to plus infinity, f of x goes to 1, right? And it's right continuous and has left limits, RCLL. This term you've seen before, RCLL, all of you? Agni, have you seen this?
Yes, I think.
Okay. And Surandan, so have you? Praveen?
Yeah.
So all it means is it's kind of, it's functions which are always continuous, at any point are continuous from the right. If you take a sequence coming from the right, you'll reach the point, and that point is actually the function value. On the left, the limits exist. It need not be the function value, but the limit will exist. It's good to get comfortable with these things. And what I've not done is, RCLL paths are actually very important for processes which have jumps, like Markov processes and all. So I've not defined a sigma algebra for them for you. I could have, it's just more complicated, it's less intuitive. So I've just done that. At the right time, if you're curious, you can look into this. So it's a very kind of, Skorokhod came up with the Skorokhod metric on this setup. It's interesting, but it's a little bit kind of complicated, so I'm avoiding that. Okay, construct a probability measure on RBR. So again, what I'll do is for any interval A of B, and now I'll assume that it's open on A and closed on B. That's important, right? So that if there's a point mass on A, that's not kept here. So P of A of B is FB minus FA. Now you can convince yourself that if I look at finite union of such intervals A and B, open on A, closed on B, then that finite union collection is still an algebra. In the sense, its complement is again of the same structure. And if I take union of these, I again have similar kind of finite union of these kinds of intervals. Okay, so it's an algebra too. So now I've been able to assign probability to on this algebra, but just by using CDF. Right. So all I really need is now suppose, for example, no, I actually do this here. So all I need is countable additivity of this probability measure on this algebra to say that okay, then I can use Cauchy-Deory's theorem and I get an extension to the whole Borel sigma algebra. Now countable additivity we proved in the interval 0, 1 earlier. We didn't prove early on the whole real line. Right? Now, you'd imagine that that should be a straightforward extension and that imagination would be correct. But I'll just tell you what the steps there are, how that happens. Just very quickly, so you can go back to this later. It is countably additive. So you can see it in Shiraya, but let me just tell you the big picture in this. So again, we need to show that P of A of n decreases to 0 as a n goes to infinity. I mean, that's, because let's see what countable additivity really means. What's going on here? Let me just open some. Okay, so what I need to show is that summation P of A of n is equal to P of union A of n equal to 1 to infinity when the ANs are disjoint. Right? That's what this means. Now I have, because I am on the algebra and I have a probability measure which is finitely additive on the algebra. I didn't prove this, but it's clear, right? If you look at the unions, my algebra is collection of union of finite intervals. So finite additivity would be straightforward, right? So what that means is, okay, so I can write P of union n equal to 1 to infinity an to be equal to summation P of am, let me call it, m equal to 1 to, let's call it k, plus P of union A of, running out of symbols now, r equal to k plus 1 to infinity. That is always true, right? Because it's algebra and I have finite additivity on the algebra. This tells me that, okay, so I can get rid of this guy and I can write right? This follows, and now it's true for every k. So this also follows. So I need to prove the other direction, but you can, maybe I kind of was too hasty, but if I just write it like this, m equal, so let me just cancel this, m equal to 1 to infinity, no, so m equal to 1 to k, P of A of m plus P of union k plus 1 to infinity, A of r, let me call it. This set here is going to 0. So what have I written here? K plus 1. So B of k plus 1 is going to 0. In the sense, anything that's in that, in that set B of k plus 1, as k increases to infinity, is going to not be there eventually. It will come out of it. So this set is going to become empty in the limit. Right? And what I want to show is that this probability of bk plus 1 is going to 0. Then I'll get equality between the two. Right? This will go to 0. This will go to its the summation limit. And then, all of this is true when I have equality. So let me just not talk about this stuff at all. Okay. So I'll get that this is going to 0, and this is, of course, converging to increasing to the infinite sum. So I get countable additivity. The left-hand side is fixed. Okay. So all I need to show basically is that given that P of A of n is, given that an is going to become empty, I want to show that P of A of n must be going to 0. Okay. And then I have countable additivity. Right? Okay. So that is for all epsilon greater than 0, there exists n of epsilon, so that P of A of n is less than or equal to epsilon for all n bigger than or equal to n of epsilon. That would do it, right? For this to go to 0. I just have to show that eventually it becomes arbitrarily small. So what I'll do is I'll just choose my n large enough so that probability of mass assigned to minus n and n complement is less than epsilon by 2. So you give me an epsilon. I'll just, because you give me the distribution function, so I can always choose minus n and n, so that outside of that, the mass is epsilon by 2 at most, less than or equal to epsilon by 2. Okay. And now, so now I've got myself restricted to minus n and n. That is fixed. Okay. So now what I'll do is I'll do the same analysis that I did last time. There was nothing special about 0 to 1 there. All I used was the fact that it was a compact set. And I'll give you n of epsilon now, so that for all small n greater than or equal to n of epsilon, P of A of n is less than or equal to epsilon by 2. So this A of n, I guess, is A of n intersected with minus n and n. Okay, so this is less than or equal to epsilon by 2. The remaining mass outside in any case is less than or equal to epsilon by 2. So P of A of n, so it's bad notation here, so you'll have to adjust a little bit. This should be, I guess, P of A of n intersection with minus n and n. Right? So this is going to be less than or equal to epsilon by 2 for all n greater than or equal to n epsilon. My previous analysis will guarantee this. And that tells me that P of A of n is less than or equal to epsilon for all n greater than or equal to n epsilon. And that's what I'm going to show, right? And hence the limit of P of A of n is going to be 0. Okay, so I mean, the point was, what was the new idea required? It was just that, I can always go far enough so that the mouse outside that is arbitrarily small. And then I repeat my analysis and I show that things are well behaved. Okay. These are very good ideas. When you want to prove things in a general setting, you kind of truncate, etc., or cap like we did, and then prove the result there and then extend this. So it's good to see many such kind of variations. Then you kind of have a way of thinking about these things. So depending on the problem, you have a sense of how to address it. So by Cachiedori, it extends to uniquely to RBR. So that's what we get now. You give me any CDF. Now we have a complete way of extending it to RBR. Right? Okay, good. So now, okay, let's now talk about probability measures a little bit more. So on R, we can have discrete probability measures, right? You just have countably many points or finitely many points, and you put mass on them. So there are points x1, x2, and so on. And you have masses p1, p2, and so on, which are strictly positive, and then they sum to 1. Non-negative, let's say, and then they sum to 1. And then P of A for any set actually is just summation Pi for all the xi's belonging to A. So this will, of course, work for any set. Now, there's no issues here in the discrete setting. Then we have probabilities measures, which are absolutely continuous measures on R. What do we mean by this? Anyone? Just so that you're not feeling left out. So what does absolute continuity mean? Or absolute continuous measure on the real line mean?
Like the measure will be continuous with respect to the Lebesgue measure. I mean, if you give me any epsilon, I can find a delta such that every set having a Lebesgue measure less than delta will have that measure less than epsilon.
So we'll define it properly later. It's slightly more elaborate than what you're saying, absolute continuity. It's not just continuity. But what it boils down to is that the Radon-Nicodemus derivative exists. And I mean, in the simplest setting, what it means is, because now we've not talked about all those things so far, it just means that there's a density function so that, f of x can be represented as integral from minus infinity to x, f of I d by. So there's a non-negative function f of I for which this is true. So now, since we've not talked about what functions are allowed, so we've not described Borel functions yet, so I'm not coming to that right now. I'll add that later. And
Are you referring to the Radon-Nicodemus theorem?
Yeah. That's right. So the Lebesgue measure, so your measure corresponding to f is absolutely continuous with respect to Lebesgue measure, then that will guarantee that the density functions such as small f exists. Right? So it's an if and only if condition. So what Agnew was trying was to give the other part of the result, absolute continuity defined in that sense. But once you define that way, then that theorem guarantees that this is f of I exists. We will do Radon-Nicodemus theorem after we've done integration theory. But right now you get an idea at least that whenever there's a density function, see, if you've not seen these things, what's interesting is that the density function needs to be defined only on a set of full measure. It need not be defined. It can be arbitrary on a set of measure 0. Like on the rational, this small f of I could be arbitrary. Won't change anything.
I didn't get you. Can you repeat it? On arbitrary small?
I'm saying on a set of measure 0, this density function can be anything. It makes no difference. This density function is useful only when we integrate it. And what a function does on a measure 0 does not affect the integral in any way.
Yes.
Yeah. So it has to be non-negative, but again, on a full measure set, it has to be non-negative outside a set of measure 0. So those are issues we'll kind of tackle more, carefully when we do integration theory. Okay, but what I just wanted to show you was this. I don't want to spend too much time on this, but still, it's instructive. It's good to see this and be clear about this. That we also have what are called singular measures. So what are singular measures? You probably heard about them, but probably don't remember them very well, right? Some of you may have heard about them. So we're not going to talk much about them, but I'll just say something. So distributions where distribution functions are continuous, but have all their points of increase at a set of measure 0. Right? So they are constant on a set of measure of a set of full measure. So then you say, okay, this is interesting. You can imagine wondering why should such measures exist? Right? It's not at all obvious that something like this should exist. So what we'll do is we'll just go through one example and then I'll leave it there. The big theorem is that any distribution function is a convex combination of discrete distribution function, absolutely continuous distribution function, and singular distribution function. So that's thing that you need to be aware of. And singular measures, I'll just show you an example of it and then we'll leave it there. I mean, there you can talk a lot more.
Tell me, what do you mean by all their point of increase?
Yeah, the points where they are going to increase. So what do I mean by that? I'll just mention that in a moment. Meaning x is a point of increase if f of x plus epsilon minus f of x of minus epsilon is positive for all epsilon.
I see. So, okay, I see.
So that's a point of increase. For every epsilon, that's the case. So clearly, if it's a finite mass that you put there, that's a point of increase. Right? But point of increase can also be that you have a positive density there. So then fx plus epsilon minus fx of minus of epsilon, it's an integral of the density function, which is strictly positive, let's say, and that's also positive. But let's take an example to see indeed a singular measure. Does anybody know how might that come up? You see an example here. Let me just ask you directly. So do you know what a Cantor set is?
Yes.
Everybody knows what a Cantor set is. Sunanda, do you know what a Cantor set is?
No, sorry.
Okay, good. Yeah, I'm hoping that I'm teaching somebody, otherwise everybody already knows. Praveen, do you know what a Cantor set is, or?
I heard it said once.
Okay, you've seen it once or twice. Yeah, it's one of those things. It's good to see it many, many times because you forget it in a couple of days. So now people who have seen it, what's the definition? Just help me.
So totally disconnected, bound, compact, and perfect set.
Oh, come on. Bring it home to us. Give us a picture.
Okay, so you have a 0-1 interval.
Mhm.
So you first cut it half. You just cut it 1/3 and remove the middle part, and then in the rest of the part you again do the same thing, and the rest of the points that you are getting, you are collecting the points and take the union. That residue set will be the Cantor set in the limiting case.
Right. So you take the interval 0-1 and take the open middle third. So 1/3 to 2/3, but open set, open interval, and throw that away. Right. And when you construct a distribution function, we'll do it later, we'll keep it constant on that open interval.
Yes.
And now, so that's stage 1. So now we are left with 2 closed intervals, right? Now we do the same thing exactly to both the intervals separately. We take the middle open third from both the intervals and throw that away. So now we're left with how many? I guess 4.
Yes.
And now we do the same thing to those 4. So we're left with 8 and so on and so forth. So every time we keep on taking the middle third out, and the points which remain. So I've not thought much about this, but it seems quite hard to imagine the points that remain. It's not just the boundary points. Because if it was just 1/3 and 2/3 point, and then, I guess 1 by 9 and 2 by 9, and then 7 by 9 and 8 by 9. If it was just those points, and I take their union, that's just a set of rationals, that's countable. So there are other points which are also remaining. I've not thought about this enough, but it seems like it's hard to imagine what those points will be. It's hard to find a mental picture of it. You can, it's worth thinking.
One way to think is
Mhm.
if you write all the points in 0, 1 in base 3.
Yeah.
And then you take only those points which don't have 1 in them.
Yeah. Yeah.
Those expansions didn't have 1 in them, only zeros and 2s.
Right. So we'll do that right now. We'll do that. I mean, it's still there. You don't get a geometric picture in your mind with that, but you get a mapping between the real line and the Cantor's. Yeah, I mean, after you've seen these things, it looks like they're kind of obvious, but when you think about it, it's not really clear. It's quite a profound set. Cantor, everybody knows about, I take it, right? Cantor's story, How much do you know about Cantor? I also know bits and pieces which I've kind of forgotten, but maybe somebody wants to say something. There's a famous Hilbert's statement, right? Nobody can take us away from the paradise that Cantor has created for us. I think this diagonal argument to prove that, okay, the numbers are countable and vis-a-vis uncountable, that was also Cantor's creation. So he gave the diagonal argument, and then he created different levels of infinity. And that idea was resisted a lot by people. There's only one infinity. What do you mean by different types of infinity? So Hilbert's comment was in this context. But I mean, the other unfortunate part is that he went mad. So anyway, that's
He
okay.
went mad and still he published paper in the asylum.
Oh, is that right? I didn't know that. Yeah.
So
Okay.
yeah,
He gets mad and go ahead.
as I remember, he has a friend outside. So in the asylum, he used to write and send the papers to them. And instead of Cantor, his friend used to publish it.
I see.
for him.
Okay, well, that's very interesting. It's fascinating. Yeah. I mean, TFI I thought was a much more intense place mathematically many, many years ago, and I've heard people kind of compare it to an asylum. So anyway. All right, so you get the picture. So take 0, 1, so you get this construction, right? So at stage n, you're removing 2 to the power n minus 1 middle thirds of all remaining subintervals. Now, how do we know that what's remaining as measure 0? So I guess you probably remember that, right? So we just count the measure of all that we've removed, right? 2 to the power n minus 1. Each of those intervals had length of 1 upon 3 to the power n. And we sum it from n equal to 1 to infinity. That's just 1 by 3 that comes outside, right? And then you're just summing up a geometric series of 2 by 3. I think it's going to be what? It's 1 plus 1 by 1 plus 2 by 3 plus 2 by 3 squared and so on and so forth. That's 1 upon 1 minus 2 by 3. So it's equal to 1. So what remains as a measure 1, as a measure 0? Okay, now k is uncountable. And how do we prove this? So this is, So for each point x in k, so this point has survived, right through. Each point x has survived the process of elimination. So at every time, at the nth stage, you assign d and x to be 0 or 1. So depending on whether at stage k, at stage n, I guess, yeah. Of construction, x was on left or right of the nearest open interval removed. Right? Because x is some point, at every stage, some interval got removed, right? From the left as well as from the right. So whichever was nearest, if it was on the left side, then you give it 0. If it was on the right side, you give it 1. And you do that for every n. I guess. So if you do it that way, you get for each x, expansion in terms of 0, 1, 0, 1. So it's an exact map to a point in an interval 0, 1. Every point in the interval 0, 1 can be written as expansion 0, 1, 0, 1, right? Binary expansion. Because I mean that point either lies in the first half or in the second half, depending on that you assign it 0 or 1, and then you fixed which half it lies in. Then in that half it lies in the first quarter or the next quarter. So that's how you decide the next term, and so on and so forth. So this is what Malhar was saying. So Cantor's set is equal to all the numbers in 0, 1 which have base 3 expansion that does not contain the digit 1. So that is Cantor's set K is C of n into t to the power minus n summation n equal 1 to infinity, for which each Cn lying in 0 or 2. So it's like, I'm going to define every point in 0, 1 as follows. First, I'll see, does it lie in the first 1/3 or second 1/3 or third 1/3? Depending upon that, I'll assign a value 0, 1, 2. And then I'll fix that 1/3 and I'll divide into again 3 parts. I'll again assign it a value 0, 1, 2. And I'll continue in that manner, right? So every point has a unique address from that. And that is captured by this, so it can be represented as a summation n equal 1 to infinity Cn t to the power minus n, where Cn can take values 0, 1, or 2. Now, all you're doing in the Cantor set is you're not assigning value 1. The middle part is always getting missing. So either the first guy is in the first 1/3 or it's in the last 1/3, not in the middle. So Cn cannot take the value 1. And that property continues throughout. It's either in the first 1/3 or the last 1/3. But nonetheless, that tells you that each point has a representation in this, what do you want to call it? In this base 3 expansion. Each point can be written as, expansion with each digit is either 0, 1, 2, 0, 1, 2, 0, 1, 2, etc. And Cantor set doesn't have the ones in between. It's just 0, 2, 0, 2, 0, 2. But then we can map them to the binary representation 0, 1, 0, 1, 0, 1, and we get the 1-to-1 mapping to the uncountable interval 0 to 1. Hence, Cantor set is uncountable because it has a 1-to-1 mapping with the uncountable set. So that's a neat argument. Okay, now let's construct a measure which is singular, whose points of increase have measure 0. Right? So you can imagine what we do is we start with, so we are going to construct and I'll just give you an idea again. But this, this should be easy to make it more rigorous. So F0x is a uniform distribution on 0, 1. That means your CDF is just a straight line from 0 to 1 with slope 45 degrees. Okay? That's your F0x. I'm going to construct a sequence of functions F0x, F1x, F2x, F3x, and the limiting function is going to be singular.
Sir?
Yeah?
Trying to divide the function in the set where we are vanishing it in each stage of Cantor set, means in each an, how you define the Cantor set, you are trying to make the slope parallel to x-axis where you are removing the interval, and rest of the we are taking the slope of if x equals to 1, and you are limiting this case and it will be increasing every point and 0 wherever.
Well, I'll just explain slightly in more detail how we get the slopes for the rest, because the slopes will be changing.
Okay. Slopes
will not always be 1. But it's clear what we are trying to do. So for F1x, F0x, we knew that at the halfway point, its value was 1/2, right? So now what we do is for F1x, we assign 1/2 value at the, we take the Cantor set out, the first interval out. So we assign this 1/2 value at 1/3 as well as at 2/3. So value at 1/2 is now pushed to be at points 1/3 and 2/3, it's kept at 1/2, and then we keep the function f1x constant in between these 2 points. So the slope changes now, right? Slope is going to be from 0 to 1/3. The function is rising to 1/2 level. So it's become larger. Similarly in the other direction. So Saurav, is this clear to you? That the slope has changed in f1x?
Right.
Okay. And now I'll continue to do the same thing. So I know the slope of this line from 0 to 1 by 3. I'll take the middle point. And now the interval which I'm taking away, I'll keep the function flat there. But the value at the middle point is the value I'll give to the earlier point as well as to a later point. And I'll linearly kind of join from there. And I'll keep on doing this. That's my f2x. Now I get f3x, f4x, and the limit of that is going to be a singular function. So now I won't do a detailed analysis of this limit. And part of the reason is because Shiraev did not do it. And I don't see any special reason to work hard and make this work. But it's probably fun to do. So you can probably see this from somewhere, or you can just try this on your own. But what you have to show is that f and fx is converging to another function, which also is continuous. And the way you show that is, so how do you show that the limit is continuous? Limit of functions is continuous. So anybody remember that? What are the ideas to which work?
If you can show uniform continuity, then it will work.
I think the right hand limit and left hand limit, we have to show that there.
So what can we say about the space C01? These are all in C01, right? These functions are all in C01.
C01 is complete.
It's complete space, right? So so you have to construct a Cauchy sequence, basically.
Uniform Gaussian.
Yeah. So if you have a Cauchy sequence, it will have a limit in the space itself. So the limit will be also continuous. So that you'll have to show here. Because it's it's not really a non-decreasing function. So it'll require some work, I guess. But things are getting close to each other, so it should not be hard to show that you have a Cauchy sequence. Actually, I should be quite straightforward. Okay. So that's why you know the limit is going to exist, because you have a Cauchy sequence, and the limit is going to be continuous. Okay. And by construction, because it's true for every one of them, f of x is going to be constant on the complement of the Cantor set. So it's constant on a set of measure 1. So hence it's increasing only at a set of measure 0. So you constructed a singular measure, right? That's what we went out to construct, continuous function whose points of increase are on a measure 0. All right. So every distribution function can be represented in the form, as I mentioned earlier, convex combination of f1, f2, and f3, where f1 is discrete, f2 is absolutely continuous, and f3 is singular continuous. Okay, now how do we assign Lebesgue measure on R? Right, up till now we've been assigning probability measures on R. Probability measures are finite. And same ideas can be used exactly to assign probability measures, general measures which are finite. Right? But now you say, how do I assign a sigma finite measure? You know what a sigma finite measure is, right? I can chop up my space omega into countably many spaces, omega 1, omega 2, and so on. On each omega I, I'm going to assign a finite measure. But the overall space, I can have infinite measure. So like Lebesgue measure, each interval has a finite measure 1, each interval between, I guess, integers, but the overall measure is infinite. So how do I do that? So you'll have to kind of play around with the argument that we have for finite measures to extend them in some way.
Yeah, you can take the space 0, 1 and use and demand that translation invariance to get natural stuff.
So there could be probably variety of different proofs to it.
Yeah.
I'm going to keep my life simple and follow Shiraev's method. But sure, no, I agree with you that one can you can think of 0, 1 and kind of patch it together and construct an overall algebra and construct a measure there. And then somewhere you have to use Carthy-Dory's theorem. Right? Okay, so I'll just walk you through the argument that I saw from Shiraev. You can also read it, but it's good to have it, might as well save your time this way. Okay, so general measure. So basically, I'm given a general distribution function, G. And G evaluated at infinity minus G evaluated at minus infinity is equal to plus infinity. If it was finite, then everything that we've done before works. Whatever we did for distribution function, everything basically goes through, nothing changes. So let's assume it's infinite. And what I'll do is, well, one idea that always works, so it's good to see that, is that you represent this G as a limit of functions which have finite measure. G itself is real value. Right? G is not something which becomes plus infinity early on. Right. Actually, is this what I'm exploiting? I forget now. Yeah, no, I've forgotten. I guess let's assume for now that if I define G on X as follows, where G of X is G and X is equal to G of X for X less than equal to N in absolute value, and it's G of N for X greater than equal to N, and it's G of minus N for X less than equal to minus N, then G on X has a finite overall measure. Let's assume that it could well be that, maybe what one really needs is the fact that G of X is defined on a compact set. It could have infinite measure, but I think let's just assume that it has finite measure. Let's stick to that for now. Because if it's defined on a compact set, it has finite measure. That makes our life very, very easy. So let's just do that. Let A be an algebra of finite union of interval AB on the real line, right? I mean, so I guess we understand what this means, right? There's no confusion. This is same as if I had kept an open interval at minus infinity. I just define it in this manner. Okay, so I have an algebra on the real line. And with this G, I know how to assign a measure on each interval on the real line, mu 0 AB. Hence, I know how to assign a measure on the algebra A, calligraphic A. And because I'm defining in this manner, I get the finitely additive property on calligraphic A. It requires some bookkeeping along finite intervals. So I'll take A1 union A2 union A3. I'll assume that they're disjoint. And I just want to argue that, okay, the measure I've assigned to the union is same as the measure I've assigned to the sum of each of these sets. And that's kind of obvious. So that bookkeeping we'll ignore. We know it can be done even if we have to think through all the details. Okay, so mu 0 I've defined on the algebra. Right? I just have to show that this mu 0 is countably additive, and then I'm done. Then Kathidori kind of gives me the complete measure. Okay, that's all I really need. So what I'll do is I'll construct
Semi-open and semi-closed.
What's that?
Why you taken semi-open and semi-closed?
Because then I get a proper algebra, right? And I don't have to worry about the fact that GB, on mu 0 AB, it's GB minus G of A. G is right continuous with left limits. So point masses at A get accounted for correctly in this manner.
But if you also take the open intervals, they will generate the same algebra as we saw.
They'll generate the same sigma algebra. So I mean, I could have said to you, no, open interval, the complement is not an open interval, right?
Yeah, that's
so algebra is closed under complement operation.
Yes, if you take so if you take a open A closed B and the complement of this set is suppose not open A minus infinity to B and take the complement of this set.
So tell me if I take minus infinity to B. Yeah. Complement of this set is okay. B to infinity. I mean, the only way around that is if you allow all possible intervals. Open, closed, semi-open, semi-closed. That would be an algebra.
I see.
Because then the complement will also belong to a finite union of those kinds of intervals. But the problem with that is then it's a little messy how you assign mass to the intervals. I mean, then I have to say, okay, depending on this happens, depending on this. I need more notation.
I see.
Yeah. So it's much easier. This way I can just say, okay, mu 0 of AB is GB minus GA. So life is easier in this sense. Okay. Now what I'll do is, I'll define mu n using Gn on the algebra A. So Gn is also a generalized distribution function, right? These are all generalized distribution functions which they don't have to, go from 0 to 1. They're just non-negative. So I can define a measure mu n, which is actually finitely additive on A, It's actually also countably additive on A. It's countably additive because we can repeat our arguments for countable additivity on a compact set. Okay, so mu n is well defined, and mu n of A of B is going to convert to mu 0 of A of B as n goes to infinity. Right? Yeah. So mu n of A is going to converge to mu 0 of A for all A in my algebra. It's just finite unions. Okay. So mu n has this property that is going to be dominated by mu 0, and it's going to converge to it on the algebra. So that's what I want to use, basically. That helps me. I want to basically show that my mu 0 is countably additive on the algebra that I have. So I'll take A1, A2, a disjoint union of sets, disjoint collection of sets in my algebra calligraphic A that are disjoint. And again, as I mentioned to you before, I'd like to show that mu 0 assigned to the countable union is just equal to sum of the measure assigned to each of the sets. And I have that, okay, mu 0 assigned to this countable union dominates the summation up till k of mu 0 ai. That part I know, right? Because it dominates the union, and then the union, because I have finite additivity, so union can be expressed as this sum right here. And since it's true for every k, it's also true for infinite. So limit as well. So this part is known to me. I just want to show that the other side is also true. That's how I get countable additivity. Right? Okay. So mu 0 a is limit as n goes to infinity mu n a. And mu n a already has countable additivity property. So that's exactly equal to limit as n goes to infinity, k equal to 1 to infinity summation mu n of a of k. So there I have countable additivity. So that's how I'm approaching this problem. Mu n, there I am exploiting the fact that there I do have countable additivity. So this becomes a clever way of doing things. So Malhar, what you were suggesting, so I don't remember these things now. I've seen something like that a long, long time ago when I was a student. It might work. It's not clear to me how hard or easy is that going to be. Okay. So without loss of generality, we'll assume that summation k equal to 0 to infinity mu 0 a of k is less than infinity. Because if it's infinite, then there's nothing to prove. Right? We have this property already. So both sides become infinite, then they're equal to each other. So let's assume that this is less than infinity, right? So now I know that my mu 0 of a is, sorry, let me change the color. I know that this is greater than or equal to this summation. So this difference is non-negative. But I also know that my mu 0 of a is just limit as n goes to infinity, mu n of a, and mu n of a is this summation that I have. Right? And I'm subtracting something finite from him, k equal to 1 to infinity mu 0 a of k. So I can bring that difference inside. So it's mu n of a of k minus mu 0 of a of k, right? Each term is strictly non-positive. Not strictly non-positive, it's non-positive. So the summation is also non-positive. So I get my result. So, I mean, yeah, the big picture here, I guess, is, it's just one step after the other. So that may not mean much. But how do you kind of tackle infinite measures? You first make them finite, and then the limit is infinite. So I'm assuming that g function is real valued. So g of n and g of minus n are real numbers. Right? They're not infinity right now. Yeah, so I'm ignoring the case where they might become infinity. Let's just ignore that for now. Lebesgue measure, that we don't have to worry about that. Lebesgue measure is going to have this property. So in particular, now we can define Lebesgue measure on the real line. Okay, so that was the point of this exercise. And we can define, I guess, yeah, Lebesgue measure, that's all we really need actually. Probability measures we could, in any case, even earlier. Okay, now let's talk about assigning probabilities on the space Rn and Borel sigma algebra on Rn. And this is, I'm not going to talk too much about this. We just need to know how to assign probabilities to the cylinder sets, right? To the rectangles, basically. And at the very least, when the measure is absolutely continuous with respect to the Lebesgue measure, when we have a density function, then this is very easy to do. We know how to assign, when the density function is given to us, we know how to compute this integrals on each rectangle and hence on each algebra. And by Cauchy-Doury's theorem, we get the extension to the whole B of R of n. So we are fine. So just an example, you've seen this distribution, multivariate Gaussian. Has everyone seen this?
Yes.
Right. So this is, so sigma inverse is there. So sigma is the variance covariance matrix. Mu is the mean matrix. All of these things you can prove. I mean, you have to prove a number of things when I show you this, right? First, you have to prove that the overall volume under Fn of x over the whole space is going to be equal to 1. That's a fairly demanding proof. Given that, you have to prove that the mean is actually going to be equal to mu in every dimension, mu1, mu2, and all that. And then you have to prove that the variance covariance matrix is equal to sigma. So all that can be done, of course, and you can read it up, but that's that follows from here. What's nicer, by the way, is you say to yourself, why is multivariate Gaussian so fundamental? And if it's so fundamental, why does it look so ugly? It's a nice play of words, I guess. But the real thing is that you have to see it in the right space. If you see it in the Fourier space or in the Mobigenic function space, then it looks enormously elegant. So Mobigenic function of multivariate Gaussian is just exponential of mu transpose t plus half of t transpose sigma times t.
Can you repeat the space name?
The statement I made?
Except the Fourier space, what did you mention?
No, so I mean, I could have looked at the characteristic function. I would have to just add I and I square there. But so I'm just looking at the Mobigenic function right now. All I'm saying is that representation is enormously elegant of this multivariate Gaussian distribution. It's exponential of mu t and half sigma square t. So in some sense, that representation kind of justifies why Gaussian is so fundamental.
Yes.
You know what I'm trying to say. If you look at the average, normalize it in the central limit theorem sense, then you'll actually look at the the Mobigenic function of that normalized variable that converges to e to the power t square by 2. And if you do this in multiple dimensions and give it a mean and the variance, it converges to this quantity. So it's a very natural thing. It's the simplest thing one can expect in some sense. So yeah, I mean, it's not really as messy as one thinks. It's actually very nicely, it's enormously elegant, but you just have to look at the right space. Okay, and now, we have the technology. So once we define with this density function, we define on the rectangles, then we get an extension to Rn and Borel sigma algebra on Rn, right? We understand all these things now. So in particular, for multivariate Gaussian in fixed dimensions, we are clear. Now we ask ourselves, okay, how things go wrong in the space R infinity and Borel sigma algebra on R infinity. Okay? So yeah, I'm not talking about singular measures and all that right now. And I guess if one was to talk about Lebesgue measure in Rn, that would again, all the arguments that we did with the G function, you can do them all here as well. The minus n to n, now you'll draw a rectangle minus n to n in each dimension. That will be your G of n. And now that's going to be finite. And you'll be able to extend, so you'll be able to define, for example, Lebesgue measure or generalized measure in this rectangle. And then by limiting operation, you define it on the whole space. So whatever we did for R, we can do for Rn, is all I'm saying here. It's quite straightforward. Okay, now let's talk about R infinity and Borel sigma algebra and R infinity. Okay. So we are going to go back to our cylinder sets. So let's calm down. Maybe I'm going a little too fast. You probably understand everything, but let's just go slow in any case. So recall the way we went to, the way we defined Borel R infinity was through the cylinder sets, right? Smaller sigma algebra, which contains all the cylinder sets. And what were the cylinder sets? They were the following form. X in R infinity says that x1 through xn lies in set B, where B is in B of R of n, right? And we could have kept B to be just rectangles. That would have been fine too. Nothing would have changed. We would still get this. It still will be a smaller sigma algebra which contains all those rectangles. Okay, I'm not saying precise things, but you know what I'm saying. Cylinder sets corresponding to rectangles. This is clear, right? We are actually looking at collection of all these x lying in R infinity. So it's infinite sequence of points, just that we are specifying them in the first n dimensions. Outside of that, they can take any possible values. All of that we are keeping with us. Just that, this B in which is the, which contains the first n elements, we could have restricted that to rectangles. It need not have been a Borel set in Rn. Okay. Now suppose we have a probability measure P on R infinity and Borel sigma algebra on R infinity. Suppose that probability measure is there with us. Somehow we come up with it, right? Then you observe, and then suppose we define Pn of B. So that's another set function. This we are defining for every B in Borel sigma algebra of Rn. And we keep it as probability which our measure P is assigning to cylinder set In of B. Is this clear? Right? Our probability measure is going to assign probability to all cylinder sets. It'll assign to all BR infinity, but in particular to all cylinder sets. From that we get Pn of B. For every n, for every B in R, B of Rn. So we got that, right? Then you can check that Pn plus 1, which is the probability measure that is being assigned to B cross R. B cross R is now a set in Rn plus 1. So Pn plus 1 will be assigning measures to that. That's going to agree with Pn of B, right? Because both B cross R and B have the same cylinder sets in R infinity. So they're exactly equal to just P of this In of B. So this consistency property will follow if we have a probability measure on R infinity. It has to have this consistency. So the nice part is that the other way around is also true. If I define Pn of B for each n and each Borel set B, then I can define probability measure on the sigma algebra containing all the cylinder sets. Let me correct myself. Then I can define probability measure on the algebra containing all the cylinder sets. So we can argue this, and I'll just show you in a moment, but if I collect all my cylinder sets, these are all subsets of R infinity, right? Each cylinder set is a subset of R infinity. If I collect all my cylinder sets defined, and that's where having B in BRN is useful. So I'm defining this cylinder set not as kind of taking rectangles, but I'm taking Borel sets to define the cylinder sets. Then if I collect them all, what I get is an algebra. And if I define Pn, P of InB to be Pn of B, these Pn's are given to me. So if I'm given probability measure on BRN for each n, I'm given probability measure on B of R square, P2, so P1, P2, P3, so on and so forth, so that they satisfy this consistency property. So now you give me, Pn of B I can get from using, for example, multivariate Gaussian probability density function. Pn plus 1 on B cross R, I can also get. Now I have a multivariate in n plus 1 dimensions, Gaussian. Remember when we defined these kind of time series? I don't know if you've seen the time series, but we kind of know how to define multivariate Gaussian. X1 is a vector of jointly Gaussian distributions. Then X2 I can come up with as a function of X1 plus some independent Gaussian. So X2 is also, X1 and X2 now become jointly Gaussian. Now X3 can be X2 plus some independent Gaussian, some linear combination of independent Gaussians. Now X1, X2, X3 are jointly Gaussian. And similarly, I can carry on X1, X2, X3, X4, and so on. Everything is jointly Gaussian and in a consistent manner. So the probability assigned to X1 through Xn plus 1 is such that the marginals of of X1 to Xn are, there's no contradiction in assigning probability to those guys. I'll just illustrate what I'm saying a little slowly in a moment. But right now, I just want to confuse you a little bit. So once I've defined this Pn and Pn plus 1, etc., and I have this consistency property, the big theorem tells me that, okay, then I have a, let me just, I forget what the big theorem is. Then I have a unique probability measure P on R infinity and BR infinity, which matches up with these guys. So let's just go through this theorem statement a little slowly. Okay. So let P1, P2 be a sequence of probability measures on R, BR, R square, BR square, so on and so forth. So, I mean, I guess what I was trying to say was as follows. Suppose my X0 is some A times normal mu sigma or mu1 sigma 1 square plus B. And then I have X1 is equal to, let's say, some, so let's call this A0, B0. I'm just going to create this as I go. A1 X0 plus B1 some N. Let's call that mu0 sigma 0. Let's call it N. Mu1 sigma 1 square. X2 is going to be A2 X1 plus B2 and mu2 sigma 2 square. So I can go on like this and construct X0, X1, X2, and so on. And I could have done this for vectors also. I need not have kept it scalar. But as I go through n steps, X0 through Xn is going to be multivariate Gaussian. Right? And X0 to Xn plus 1 is going to be multivariate Gaussian. So they will induce a probability measure on Rn, then on Rn plus 1, so on and so forth. Right? So those are kind of probability measures we have in mind here. So suppose we are given probability measures P1, P2, sequence of probability measures on R, R2, and so on, with the consistency property. So Pn plus 1 on B cross R agrees with Pn of B for all n for all Borel sets B in B of Rn. Okay. So then there exists a unique probability measure P on R infinity and B of R infinity, such that the probability mass that P assigns to cylinder sets INB is equal to Pn of B for all n and all B in B and Borel sigma algebra of Rn. Okay. So now you can see why this makes sense, right? I can now have a kind of infinite collection of time series of these Gaussian processes. That's what Gaussian processes are, right? X0, X1, X2, and so on. I define the marginals for them. I mean, I define distribution of each of them, X0, X1, X2, so on and so forth. And those will induce a probability measure Pn plus 1, and so on and so forth. And now I want to talk about probability of the whole sequence together. And this theorem, this theorem helps me get that. This is actually called Kolmogorov's extension theorem in R infinity. There's a much kind of a refined version of this, which is Kolmogorov's extension theorem to uncountably many dimension spaces. That I'm not going to cover. That Shrive is given. You can have a look at it. It's useful because we want to talk about Brownian motion and all of those things. Continuous time processes, and then this becomes useful. I mean, all of these are kind of useful, as I've been kind of saying, that if you want to, for example, model waves, let's say, or so, then how they're rising and falling over time. So it's kind of a stochastic process, but it's a stochastic process for waves, for example, it's on the domain is the R square, right? And maybe the value of the function is just the height, or you can have more things attached to it. So you need to model all these things. So people actually do that. They will fit such a large process, a field they call it, and then you kind of somehow have some measurements, and you use those measurements to kind of fit the parameters, etc. I mean, you want to say that, okay, one point and second point waves are going to be correlated. So Gaussian process, which allows you to model those correlations, and then the correlation decays as you go further. And then the concern is, okay, is the correlation decaying very fast, or is it decaying slowly? So do you have long range dependence or short range dependence? So all of these are very kind of common things people do in probability theory. So first issue is, how do you construct these processes? Can I construct them? Then you talk about their behavior. But Gaussian processes are typically very common because those are easy to construct. So you assume that any joint distribution of at finite locations, that is Gaussian, that is multivariate Gaussian. So you construct processes which have this property. It's very, very common. And then the correlations can decay fast, or they can decay slow. That changes the behavior of the process overall. All right. Yeah. So how do we prove this? So any suggestions on how to prove this? So we are now starting with P1, P2, P3, and so forth, right? And we have this consistency property with us. So now we have to construct a measure on R infinity and BR infinity. So we'll assign, basically, we won't assign measure to BR infinity, but we'll assign probability to cylinder sets, right? So we'll construct a measure P on any cylinder set. So cylinder set comes with the dimension N and the Borel set. So we are given that probability to us already. So that's how we assign probability to a cylinder set. So let's do this. So P assigned to cylinder set IN of B, will assign a probability Pn of B. And consistency condition ensures that we don't run into contradictions. It's not like in this way we are assigning two different probabilities to the same set. So that we are not doing. So now we have probability assigned to each N and each B. And now I collect all these cylinder sets. And the point is that collection is the algebra. So we just see that in a moment. That collection is an algebra which has finite additivity property of the probability measure, right? And then we just have to show that the probability measure that we define on this algebra is actually countably additive. And then Cartier-Dori will carry us through. So now you get to say, okay, Cartier-Dori is not just some small theorem, right? It's doing big things for us. It'll carry us through and give us the whole probability measure on the whole sigma algebra. All right. Okay, so R infinity denotes the collection of all cylinder sets. And you can convince yourself it's an algebra. If I give you A1, A2, A3, these cylinder sets, A1 corresponds to dimension 3, A2 corresponds to dimension 7, A3 corresponds to dimension 27, then all these sets can be thought of as cylinder sets in dimension 27. Right? And now in dimension 27, I do have an algebra. If I take A1 union A2 union A3, they will have their corresponding Borel sets B1, B2, B3. So I have a cylinder set corresponding to B1 union B2 union B3. So let's just see this. Okay. So take, I don't know if I'm going to say this here, but B1 through Bn are cylinder sets with sense B1 through Bn. And I'm going to assume that there exists a case so that B1 through Bn belong to. So I guess what I'm saying is B hat 1 is a cylinder set in some dimension, let's call it n1, and the Borel set in B of R of n1 is B1. Right, so I need language for this. I've not created it, but let's just say that B hat 1 has a Borel twin, call it B1, and B hat 2 has a Borel twin, call it B2. So I've got these B1 and B2 and Bn now, and I'll assume that they all belong to B of R of K. So K is the largest of these dimensions, and I extend them to that. Then, okay, then I know that their union also belongs to PR of K. If they're disjoint, then their union is going to be disjoint. So it's an algebra for sure. That's no issue there. Now I talk about the probabilities that I'm assigning to this union. Right? That is exactly under P of K, probability assigned to the corresponding Borel sets, union of I equal to 1 to n. Right? Because the left-hand side, this is a cylinder set in B of RK. So how did we assign probability to the cylinder set? We went to P of K and saw what probability was assigned to the corresponding union of the corresponding Borel set of the cylinder set, which is exactly union of BI, I equal to 1 to n. Is this clear to everybody? Right, B hat 1 is a cylinder set in kth dimension. Basically, it's all the points which lie in B1, x1 through xk lie in B1. B hat 2 is all the points x1 to xk which lie in, are infinity points, so that x1 to xk lie in B2. So B hat 1 and B hat 2 to be disjoint, B1 and B2 have to be disjoint. Right? So B hat 1 union B hat 2 is a cylinder set corresponding to B1 union B2. You can work this out. It's not a big deal. It's just a lot of notation floating around. So then I look at what was P of K assigned to this union. Because they were disjoint, this was exactly summation I equal to 1 to n, P of K of B of I. Right? And this is exactly how I assign probability to cylinder set B hat of i's, right? P of B hat of i's was PK of B of I. So I get that this is equal to this whenever B hat i's are disjoint with each other. So I have an algebra on which I've defined a finitely additive measure P. Now I'll argue that on this algebra, this measure P is actually countably additive. And again, we have to go through similar arguments that we went through earlier, but now we are in infinite dimension space, so we need to be more careful. So it's good for you to see those arguments, This is all from analysis. And once I have that, then I'm done. Because, BR infinity is exactly the smallest sigma algebra, which contains all the cylinder sets. So if I define a countably additive measure on the algebra, it uniquely extends to a sigma algebra. Are we doing on time? Chalo, it's a fairly demanding argument. So let's just take it up next time. Okay, it's a slightly more than kind of, just nested set theorem that we used earlier. You need to be more nuanced about that. But otherwise, you're doing the same thing. You say to yourself, I have these sets B hat 1, B hat 2, B hat 3, which are disjoint. I'm looking at their union, right? And maybe I don't, countable additivity again boils down to looking at these sequence of sets which are decreasing and becoming empty. Then I want to argue that the probability assigned to these sets is also going to 0. Yeah, so that's the result I want to show. But then I will not look at these sets. I'll kind of look at some compact sets which are arbitrarily close to these sets. Because when I take the intersection of compact sets, I can see a lot more. So those are kind of ideas we're going to use. It's a nice argument to see. Yeah, and all of these are useful when you do kind of, slightly more applied probability, in the sense we're applying to probability in real world and proving theorems about it, whether it's in learning theory or whatever. If you want to say these things in general settings, then these tools become useful. If you restrict yourself to Bernoulli variables or some simple random variables, then you don't need all this. But you have the intuition that all of this should be said more generally, then what I'm going to say becomes useful. So that's where the analysis tools that you learn are handy. Okay, this is all from Shiraev. I think this will be probably the last thing we do from Sharia.
Can you just repeat? Just I forgot the name of the theorem that you can extend for uncountable.
So this was the, I guess, so let's see. You had used the Hein-Borel theorem to prove the nested set theorem, right?
Yes.
If we have kind of
Yeah.
So we'll do a general version of the nested set theorem here in
Okay.
infinite dimension settings. The nested set theorem we had done when each set was in R.
Mhm.
Now we'll look at more general sets when you do that.
Okay.
You'll see this in Shiryaev, and as I'm saying, this is the last thing we use from Shiryaev. But I'll give you a homework after that, I guess, maybe in the next class. So, and that will be from Shiryaev, so you will need that book. Shiryaev has nice problems. Many of these books which do measure theory don't, and probability don't really have such nice problems in the back. So any other comments? All right. Okay, so let me just close the computer, I guess, stop recording.